So another term that you hear a lot when people are talking about coordination complexes is what's called the chelate effect. So ligands that bind to a metal at one point are called unidentate or monodentate. And that's from dent, which is tooth, so one tooth. Now, if a ligand attaches with two or more points of attachment, it can be called a chelating ligand. And this comes from the Greek. Chelate is claws. So if it's attaching with more than one point of attachment, if the ligand is grabbing on, it's like a claw, and that's called a chelate. So if you have 2 points of attachment, that's called bidentate. And even if you've never had a unit on transition metals before, I bet that you can answer this without me even telling you. What do you think tridentate might be? 3. Tetradentate? 4. Hexadentate? 6. So sometimes this would be a little question on the final. Please don't get this wrong. This was my gift to you. Right? You knew it even before I taught it. So this should be something that you can definitely get a couple extra points on the final. All right, so chelates bind with more than one point of attachment, and metal chelates are unusually stable. And this property is due to favorable entropic factors. So we're back to entropy. We're back to thermodynamics. And this has to do with the fact that when a chelate binds a metal, it releases a lot of water. And that makes the chelate pretty stable. So let me give you some examples of chelates, and then we're going to come back and think about the chelate effect again. Of course, you know it, vitamin B12 has a chelating ligand associated with it. So cobalt is in the middle of vitamin B12, and it has a ring system around it. And the ring system has these nitrogens. The nitrogens are the donor ligand to the cobalt. And so this ring system is attaching at 4 points. So it's a tetradentate ligand. There are also 2 other ligands attached to vitamin B12. There's an upper ligand shown here, which is 5' deoxyadenosine, and a bottom ligand, which is a dimethylbenzimidazole ligand. So let's take a look. This is the cartoon, but let's look at another model for this here. So we have a ring system. We have this upper ligand and then a lower ligand down here. And so the middle ring system is a tetradentate chelate. Overall, at the cobalt metal, what is the geometry of this system? It's octahedral, right. So we have this sort of square, in the middle part is square planar, but the 2 upper and lower ligands make the whole thing an octahedral system. So this is an example of a naturally occurring chelated complex. So this structure is actually fairly complicated for a vitamin. It's one of the most complex vitamins that's known. And I thought I'd just mention just a moment of history. So this structure was determined by Dorothy Hodgkin, who was a crystallographer in England. And she started working on this in the late 1940s. And people told her she was crazy, that something this large could never be solved by these X-ray diffraction techniques. And of course, now people are solving today's structures of things like the ribosome. So we've come a long way with crystallography. But she was one of the first true believers that X-ray crystallography was a powerful technique. And so she went ahead, despite what everyone said, and determined this structure. And for this work and for some other things, she was awarded a Nobel Prize. So this was a really significant contribution in the early 1950s and late 1940s. She had graduate students that she inspired. Some of them went on to become famous crystallographers. Other ones were not so successful. Crystallography is hard, and it's not for everyone. She was actually known also, Dorothy was, for her work in the Third World and her liberal politics. But one of her graduate students did not agree with her politics, but they were still friends. So this is just a message that as you go through your career, Margaret Thatcher